Welcome. In this lecture, let us begin module number 5. Module number 5 is on phase equilibria. We all know what phases are. The three phases that we are looking at in this particular course are the solid, liquid and the gas or the vapor phase, and we are going to look at the equilibria that concerns these phases in this particular module. The last two modules, we had looked at pure components first and then the solutions. The last two modules address the thermodynamic properties of first pure substances, that was module number 3, and then module number 4 looked at solutions or mixtures, which are essentially the things that arise when you put a lot of pure substances together, a minimum of 2 pure substances together. Now we have the background to address them, that is the pure substances as well as the mixture of pure substances, and it is natural for us to look at the next aspect, which is the equilibrium condition, and of course the thermodynamics associated with the equilibrium condition. A little while later I will tell you what equilibrium actually is, what is the nature of the equilibrium and so on. Very briefly now, let me tell you that the equilibrium condition is the limiting condition that can be expected in any process. Any process is expected to ultimately reach equilibrium, and it is helpful to know the limiting values in a bioprocess for its design and operation. If you just leave a process alone, it might attain equilibrium maybe in a few milliseconds, microseconds, or maybe over years, but it is good to know the limiting value so that we can design keeping that in mind, knowing that that is the maximum that we can achieve, and whatever we are going to actually achieve would be some fraction of what is maximally achievable. This module will deal with equilibria when no reactions take place, and the next module, module number 6, will address equilibria associated with reacting systems. Therefore, in this particular module we will not consider any reactions at all. Let us go back a little bit to familiarize ourselves or recall whatever we did in module 2, because it becomes necessary here in the context of phase equilibria. We saw in module 1 that the information on phases at equilibrium can be obtained from either the pressure versus temperature diagram or the pressure versus the specific volume diagram. If you recall those figures, we will take a look at them again here. This is the PT diagram, and of course this is only for a pure substance, which means only one type of substance. We need to interpret this, as we saw earlier, as the space consisting of certain values of temperature and corresponding values of pressure. This is the sublimation curve, which is essentially a demarcating line between the region where the solid exists and the vapor exists. This is so on this line you expect the conversion from the solid phase to the vapor phase or the gaseous phase. This is the fusion curve or the fusion curve, which is the demarcating line between the solid phase and the liquid phase of one substance, one pure substance, and therefore along the fusion curve we can expect the transition, which means that if a substance is going from the solid to the liquid vapor, that can happen only along these combinations of temperature and pressure, x axis, y axis. So T comma P is each point here, that can happen only along the fusion curve. Similarly, this is the vaporization curve, which is a transition or a limiting line between the liquid and the vapor phases, and therefore if a liquid becomes a vapor, it has to happen under these conditions or these combinations of temperature and pressure. And we have also seen, for completeness sake, that this is the critical point where beyond which the critical phase exists, which means above the critical pressure and above the critical temperature we have the critical phase, which is very interesting in itself, but we will not address that in this particular course. Therefore, this essentially in this course we will essentially look at solid, liquid and vapor phases and the demarcating regions. In contrast to this, if we look at pressure versus the specific volume diagram for a pure substance, we saw that these combinations of specific volume and pressure would yield in a solid, would result in a solid. These combinations of specific volume and pressure would result in a liquid, and these values of specific volume and pressure would result in a vapor. And there are regions, unlike the PT diagram, where there were lines, combinations of temperature and pressure where the transition took place. Here we have regions over which transitions from one phase to another phase take place. For example, this region is the transition over which this is the region over which the transition from the solid to the liquid phase takes place. This is the region over which the dome is the region over which the transition from the liquid to the vapor phase takes place, and so on. We had already mentioned this, a PT or a PV diagram provides the information on the phases that exist at particular conditions of temperature and pressure, typically for a pure substance. For example, at atmospheric pressure, we said that only at a certain conditions of pressure, temperature and specific volume do these transitions exist. At atmospheric pressure, 1 atmosphere pressure, H2O or water is a gas above 100 degrees C, a liquid between 0 and 100 degrees C, and a solid below 0 degrees C. At 100 degrees C, at that particular temperature, liquid and gas of H2O can coexist. We are all talking about atmospheric pressure here. And at the triple point, which is about 0 degrees C for water, all the three phases such as solid, liquid and vapor, they coexist. Now we need to distinguish this pure substance from what we normally come across, which is a mixture of pure substances. I have given this example before, and just to drive home the point clearly, let me give it again. When we have a mixture of pure substances, say water and air, this is something that we find around us all the time. There is air and there is some water vapor in it. And if we note this, the air itself consists of different species, nitrogen, oxygen, carbon dioxide and so on. And therefore, this mixture of water, vapor and air contains all these plus water vapor. When we have such things, the behavior of course is going to be different. Therefore, we should not make the error of extending the phase diagram for a pure substance to that for mixtures, and it happens without us realizing, and that is the reason why I am making the point here, especially in the case of water and air. Okay, please note this. Thermodynamics provides us with a criteria for different phases to exist in equilibrium. It tells us a priori when they will be in equilibrium, and that is the power of thermodynamics. It is a dynamic equilibrium when changes at the micro scale balance each other so that there is no change at the macro scale. At the equilibrium conditions, things do take place, processes do take place, but the rate of the process in one direction equals the rate of the process in the other direction at the micro scale, and therefore both the rates cancel each other, and net at the macro scale we do not find any major difference. What I mean by this is, consider the evaporation of water. when the liquid water becomes or gets into the vapor phase, there is movement of water molecules from the liquid to the vapor, and let us say under a given set of conditions that takes place at a particular rate. Here there is no air, by the way, just water and vapor, a pure substance. So the liquid water becomes vapor. At the same time, there is water vapor there, some of those molecules may not have enough energy and they will get back to the liquid phase. So there is a rate at which liquid water becomes gaseous water, and there is a rate at which the gaseous water becomes liquid water. And what happens at equilibrium is that these two rates match. That is all that happens. There is still continuous motion or movement of liquid water to vapor water, and there is still motion from the vapor phase to the liquid phase. These two rates match, and that is why we call it a dynamic equilibrium. For the purposes of this course, let the phases be indicated by alpha, beta, gamma and so on. Might need more, and in a minute we will see why. They could be multiple phases of the same kind, that is why we need more. For example, we all know that or we may know that proteins are purified or extracted through a process called aqueous two phase extraction, where we have two liquid phases, two aqueous liquid phases. So you can call one alpha, the other one beta and so on and so forth, and each of those phases consist of several components, and let the components be indicated as 1, 2, 3 and so on. Now comes the criteria that thermodynamics gives us for thermodynamic equilibrium, and for thermodynamic equilibrium the following equations must be simultaneously satisfied. The temperature of the alpha phase must equal the temperature of the beta phase, must equal the temperature of the gamma phase and so on, which means that the temperature of all the phases has to be equal. That is the first condition for thermodynamic equilibrium, and we will call that equation 5.1. Secondly, the pressure of the alpha phase must equal the pressure of the beta phase, must equal the pressure of the gamma phase and so on. In other words, the pressure of all the phases in equilibrium must be the same, or in other words, only if the pressures are the same can we call the phases to be in thermodynamic equilibrium. We will call that equation 5.2. Also, remember the chemical potential that we talked about. The chemical potential of component 1 in the alpha phase, note this, we are talking of chemical potential of a certain component, and certain component in the alpha phase mu 1 comma alpha must equal the chemical potential of the same component in the beta phase, that must equal the chemical potential of the same component 1 in the gamma phase and so on and so forth. In other words, the chemical potential of a certain component must be the same in all the phases that are present at equilibrium. We will call this equation 5.3. The other things are quite easy to see. The chemical potential of the second component must be the same in all the phases. Mu to alpha must equal mu to beta, must equal mu to gamma and so on and so forth. We will call this equation 5.4. Same thing continued. Let me write one more and put dot 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 later. Mu 3 in the alpha phase must equal mu 3 in the beta phase, must equal mu 3 in the gamma phase, and must be equal to the mu 3 in each of the other phases. We will call this equation 5.5 and so on. We will have the number of these equations being equal to the number of components that are present in the system which consists of phases in equilibrium. To repeat, the temperatures have to be the same across phases, the pressures need to be the same across phases, as well as the chemical potential of each component must be the same across phases. These are the conditions for equilibrium, and we can use it both ways. We can use it to check whether equilibrium is achieved, we can use it to predict when equilibrium will be achieved. Now, let us look at something that will be useful. You may have done this in earlier classes, but it is good to know clearly what this really is and the basis for this. That is why we are doing it here. It is nothing but the phase rule for non-reacting systems. In this module we are considering only non-reacting systems, therefore, we will consider phase rule for non-reacting systems here. Let us consider a system containing pi number of phases, gas, liquid, vapor, solid, and so on and so forth. Let us say in general it contains pi phases, and we also saw it is just not limited to these phases. They could be two distinct liquid phases, there could be many distinct liquid phases, there could be many distinct solid phases. It is a little difficult to imagine different vapor phases, but certainly there could be different liquid phases and different solid phases. Therefore, let us say in general that the system contains pi phases, and let the components in each phase be C, and we are going to implicitly assume that each component is present in each of the phases, or each component is present in all the phases. If the number of components in each phase is C, we know that the mole fractions or the mass fractions need to add up to 1. For example, if the mole fraction is x1, x1 plus x2 plus x3 and so on till plus xn must equal 1. So, this automatically gives us a relationship to be satisfied between the concentrations of the C components in each phase. Therefore, the composition of the phase is specified by C minus 1 variables. Suppose there are 5 components, we need to know the concentrations of 4 components, and the last component we can always get by adding the mole fractions of these 5 and equating it to 1. Therefore, if we have 4, we can always find the 5th one. Therefore, the composition of a phase is specified by C minus 1 variables. In addition, the temperature and pressure need to be specified, because they are conditions of equilibrium. Equality of temperature and equality of pressure across phases are conditions that need to be satisfied for equilibrium, and therefore, the total number of variables that need to be completely that are needed to completely specify a phase is C minus 1 plus 2, that equals C plus 1. That is C minus 1 variables of composition we saw, plus 2 variables temperature and pressure. You add these two together, you add all these together, you get C plus 1. And we said that each of these component is present in all the phases, and the total number of phases is pi, and therefore, the total number of variables needed to specify the state of the system, but not its size of course, is pi phases times C plus 1 variables that are required to specify in each phase. Therefore, pi into C plus 1. If the various phases of the system are at equilibrium with each other, then the conditions of equilibrium can be applied. That equations phi 1 to phi 5, which is T alpha equals T beta and so on, P alpha equals P beta equals P gamma and so on, and the chemical potential of each component in each phase must be the same, or of each component in the phases must be the same. There are C equations for chemical potential, one for each of the C components that are present, that we saw. If we have we wrote mu1 alpha equals mu1 beta equals mu1 gamma, then mu2 alpha equals mu2 beta equals mu3 gamma, mu2 gamma and so on, mu3 alpha equals mu3 beta and so on. So, you have C such equations if you have C components. Therefore, we have C equations for chemical potential, one for each of the C components and one each for the temperature and pressure, T alpha equals T beta equals T gamma, P alpha equals P beta equals P gamma, and therefore, we have a total of C plus 2 equations, and each of those equations corresponds to pi minus 1 separate equations, because T alpha equals T beta is one equation, T alpha equals T gamma equals another equation, and so on and so forth. Therefore, each of those equations corresponds to pi minus 1 separate equations, and therefore, the number of equations between the variables is pi minus 1 separate equations into C plus 2 equations. Why did we do all this? It is because of this. We know that for a meaningful solution set, when you are trying to solve knowing some set of variables and we are trying to solve for the other set of variables that are unknown, for a meaningful solution set, the number of variables must be greater than or equal to the number of independent equations, otherwise we do not get a unique solution. Thus, pi into C plus 1, number of variables that we saw earlier, must be greater than pi minus 1 into C plus 2 equations for a general case. We have completely generalized this. We said pi phases and C components, and we got the number of variables as pi into C plus 1, we got the number of independent equations between them as pi minus 1 into C plus 2, and we are using the mathematical criterion that the number of variables must be greater than or equal to the number of independent equations between them if we need to solve them uniquely. Therefore, pi into C plus 1 must be greater than or equal to pi minus 1 into C plus 2. In other words, if you transpose this, C minus pi plus 2 must be greater than or equal to 0. You can do the transposition and indeed find that C minus pi plus 2 equals 0 or is greater than or equal to 0. We will call this equation 5.6. The left hand side of 5.6, which is this C minus pi plus 2, this can be interpreted as the number of independent variables that are needed to completely specify the system, or in other words, the number of degrees of freedom for a given system, and let us indicate the number of degrees of freedom by f, and therefore f is nothing but C, number of components, minus pi, the number of phases, plus 2. This is the number of variables that are needed to completely specify the system. Let us call this equation 5.7, and some of you would have already realized that this is indeed called the phase rule, and application of the phase rule tells us the number of independent variables that are required to completely specify the state of a system if the number of phases and components are known. And of course, we have assumed the equilibrium conditions. We have written the phase rule for pi phases in equilibrium with each other. To get more comfortable, let us do this example. Find the number of independent variables that are needed to completely specify the state of the following systems: a pure component in a single phase, that is the first system; a pure component that is present as a mixture of liquid and vapor. Please take about 10 minutes. We have done a few things till now in this particular class. Please take a few minutes, go back and see what we have done and see what you need to solve this particular example. Take about 10 minutes for that. I will come back and tell you the solution. Go ahead, please. This was a straightforward application of the phase rule, therefore most of you would have gotten the solution already. The solution is as follows. We said the first system is a pure component, which means C is 1, single phase, which means pi is 1, and therefore C minus pi plus 2, and this cancel, we get F equals 2, and therefore both temperature and pressure need to be explicitly known. F essentially implies the number of independent variables that are needed to fix the state of a particular system, and typically temperature and pressure can be taken to be those variables of choice. The temperature and pressure need to be explicitly known to completely specify the state of the system. The second example was if the system is a pure component, between C equals 1 in 2 phases, pi equals 2, then F equals C minus pi plus 2, and that turns out to be 1. In this case we just need one variable, say temperature or pressure, and that is the only thing that is needed to completely specify the state of the system. The temperature, what this also means, or another way of looking at this, is that the temperature can be freely chosen, but the pressure, or excuse me, the pressure can be freely chosen, but the temperature cannot be freely chosen. It has a definite value for a particular other variable. For example, if the temperature can be freely chosen, the pressure will have a definite value for the chosen temperature. If the pressure can be freely chosen, then the temperature will have a definite value for that chosen pressure. Okay, let us begin to look at one of the fundamental relationships when we consider phases in equilibrium, especially when transitions between phases take place, and that is called the Clausius-Clapeyron equation. We are going to start doing this, and let us see how far we get today. Let us consider our system as a pure substance. We will start with pure substances, that is good to understand the basis. Let us consider our system as a pure substance in 2 phases, say alpha and beta at equilibrium, and what I would like you to note is that we have not specified the nature of the phase. These alpha and beta could be any 2 phases, they could be liquid and vapor phase, liquid and solid phase, vapor and solid phase. That is what is given here. The following discussion, unless indicated otherwise, is applicable for any 2 phases. They could be vapor liquid, solid liquid, solid vapor. Since the phases are in equilibrium, at those conditions of temperature and pressure, which we will indicate by the superscript 1, we can certainly write from the condition of equilibrium, the first 5 equations, equations phi 1 to phi 5 and so on, mu alpha at the conditions specified by the temperature and pressure, we will indicate that by 1, must equal mu beta, which is the chemical potential of the pure component in the other phase, in the beta phase. This is the chemical potential of the pure component in the alpha phase at certain conditions of temperature and pressure, must equal the chemical potential of the same component in the beta phase at the same conditions of temperature and pressure. This automatically comes from the condition of equilibrium. Let us call this equation 5.8. In the neighborhood of this point, which means a very small region around this point, mathematically speaking, where the equilibrium conditions can be considered to exist. It is a hypothetical situation here, but we need the concept of neighborhood to completely develop this particular concept. Therefore, in the neighborhood of this point where the equilibrium conditions can still be considered to exist, we can write mu alpha 1 plus d mu alpha, that is a change from the point 1 in the neighborhood of point 1, equals mu beta 1 plus d mu beta. Of course, from 5.8 the previous equation we know that mu alpha 1 equals mu beta 1, therefore, they can be cancelled, and therefore, d mu alpha equals d mu beta, the differential of mu alpha equals the differential of mu beta. Let us call that equation 5.9. Since the chemical potential of a pure substance is a function of only temperature and pressure, we can write equation 5.9 in terms of the expanded functionalities. This is the total differential, writing it in terms of partial differentials from the theorem in mathematics. D mu alpha is dou t of mu alpha at constant pressure dt plus dou p of mu alpha at constant temperature dp. This is d mu alpha. This equals dou t of mu beta at constant pressure dt plus dou p of mu beta at constant temperature dp. Let us call this equation 5.10. Now, let us take a slight detour to establish a few things, and then we will come back to our two phases and so on. From equation 2.15 that we saw earlier in the module number 2, dgt equals minus st dt plus vt dp. You recall this equation now. By now you must be familiar with this, since we have seen this so many times and used it also. Plus, of course, this is a multi component system, therefore, sum over all I mu I dni. This is the equation 215 that we saw earlier. Recall the reciprocity relationships that we again saw in the second module. Following the reciprocity relation, doing the reciprocity relationship for equation 215, the following relationships can be written out. Dou mu I dou p at constant t and ni equals dou vt dou ni. Now, we are doing the reciprocity between these two. Dou mu I dou p at constant t ni equals, dou vt dou ni at constant t p and all other n j's which are different from ni. We can write this, and that equals, this is nothing but the definition of the partial molar volume VIT hash. Let us call this equation 511, and if we do the reciprocity between this and this, we can write dou mu I dou t at constant p ni, dou mu I dou t at constant p and ni equals minus dou st dou ni at constant t p and all other n's which are different from this I, or all other nj's where j is not equal to I. And what is this? This is nothing but the partial molar entropy SIT hash. Hash is somewhat missing here, SIT hash. We will call this equation 512. Further, if equation 2.3, which can be written for the total values as Gt equals Ht minus Tst, this is the definition of Gibbs free energy, and we are writing this for the total values, not for a single mole. Gt equals Ht minus Tst. If this is differentiated with respect to Ni at constant T and P and all other Nj's, we can write in terms of partial molar properties as Git hash equals Hit hash minus Tsit hash. Now, we are differentiating each term with respect to Ni at constant Tp and Nj, and by definition that derivative would be Git hash. By definition, that this derivative would be HIT hash, and this one would be minus T SIT hash. We will call this equation 513, and from equation 216 we get GIT hash equals mu I, the partial molar property with respect to the single mole there, therefore, we get it equal to mu I, and therefore, from equations 514 and 512, equation 513 from 514 and 512, 514 is this GIT hash equals mu I, and 512 was this, which is the which we obtained from the reciprocity relationship. From these two equations we can write mu I equals HIT hash plus T dou mu I dou T at constant P n I, which can be rearranged as, I am just rearranging this by T dou mu I dou T at constant P n I minus mu I, and I am dividing this by T squared, is nothing but minus HI, now I have taken this to the other side, minus HI T hash by T squared, just a rearrangement. There is a reason for this rearrangement, or the reason for this rearrangement is this form is nothing but dou T of mu I by T P n I. If you are unable to see this, consider this as U by V, or numerator by denominator, denominator function into derivative of the numerator function minus the numerator function into derivative of the denominator function, which is 1 here, divided by the square of the denominator function, and that is the derivative dou mu I by T dou T at constant P n I equals minus HIT hash by T squared. We will call this equation 515. For a pure substance, the partial molar properties are nothing but the properties per mole of the pure substance, they kind of coalesce into each other, and thus the equivalent equations of 511, 512 and 515, when we write down the equations you can recall those, or you can go back and check what 511, 512 and 515 are. Dou mu by dou P at constant T equals V, equation 516, dou mu dou T at constant P equals minus S, equation 517, and dou mu by T dou T at constant P equals minus H by T squared, equation 518. Our 511 was when you had a I here and a VIT hash here, 512 was you had a I here and SIT hash here, and you had to take other ends also as constant, and here you had a I and HIT hash here and P and other ends to be constant here. Therefore, since these are written for a single mole of the pure substance, we can drop all these I's and hashes and so on, because the partial molar property becomes the property per mole of the pure substance. What we will do when we begin the next class is we will get back from this detour. We essentially wanted to come up with these relationships, and that is why we took a detour. When we begin the next class, we will get back to considering the two phases in equilibrium and the process of transfer from one phase or transition from one phase to another, which is the context of the Clausius-Clapeyron equation. See you in the next class.